We're off to do the limit comparison test. If you have any trauma in your life from the direct comparison test, hopefully that's starting to heal up and you're feeling better about it. And the good news is the limit comparison test is going to be a lot easier because now you're used to such an awkward process and it's just easier. A disclaimer from the math lawyers, and the same thing for the direct comparison test. You're only allowed to use the limit comparison test if all terms in the series are positive. I don't know how much I emphasize that on the direct comparison test because we had enough to do on that one. And just like the direct comparison test, the limit comparison test, you'll have an actual series, and then out of thin air, guided by your intelligence and practice, you will choose a comparison series. And like the direct comparison test, you'll choose this comparison series based on a hunch on whether or not the actual series is convergent or divergent. Once you've chosen your comparison series, you're going to set up a limit that's a fraction of your two series. And it doesn't matter if you put the comparison series on the numerator or the comparison series on the denominator. You go whatever path you want, but you're going to compute that limit. Once you compute that limit, you're going to come up with a value. If that value is a number that's bigger than 0 but smaller than infinity, then you will come to the conclusion that both of those series either converge or both of those series diverge. You might think, well, that's crazy. Well, how am I going to know if they converge or diverge? Well, you will know because you've chosen a comparison series with the convergence or divergence in mind. If you're suspecting divergence, you'll choose a divergent comparison series, and you'll know your comparison series is divergent. So, if you chose a divergent comparison series and you go through this process and you end up with a value right through here, then you know both series have the same characteristics, either convergence or divergence. And since you chose a divergent comparison series, you know both series diverge. And if you know both series diverge, you now know that this is a divergent series. So as you would guess, if you thought this was convergent, you would choose a convergent comparison series. You'd go through this limit process, and if you got a value between 0 and infinity, we would then say both of those series have the same characteristics, and in this case, we would say they both converge. I chose a convergent comparison series. It then forced the logic that my actual series converges. If you don't get a value from your limit, that's a number between 0 and infinity, and most of the time what would happen in that case is you'd get an infinity, maybe a 0, then you can just not draw a conclusion in that scenario and you just have to go find a different test. We'll work a couple of examples. In this case, I look at this series and I'm thinking, boy, would that be convergent or divergent? And I have to do a little bit of intelligent daydreaming here. As I approach infinity, it seems like my denominator is stronger than my numerator. But if I think a little deeper about it, it's stronger by 1 exponent than my numerator. So in my mind, this is kind of like a 1 over n series, which is a divergent harmonic series. So if I had to take a guess right now, this thing with a little algebra reduction, eyeball adjustment, is kind of like that. So I'm going to suspect divergence. I may or may not be correct, but that's what I'm going to suspect. So when I choose a comparison series, I should choose a divergent comparison series. And my advice to you is choose a series that seems pretty related to the form that I'm in. So this, with some algebra adjustments, is really that, which means that would be a heck of a comparison series to use. So I've chosen a divergent comparison series. That means I'm suspecting divergence here, and now I'm going to go do the limit and see if the math checks out, as Homer Simpson would say. That limit sure does look clunky, but it'll get better. Now, like I emphasized before, you can go comparison series in the denominator, comparison series in the numerator. It doesn't matter. they're both going to lead to the final same conclusion. So I'm going to choose the limit on the left for no good reason. And when I divide by a fraction, it's like multiplying by the numerator, or by multiplying by the reciprocal. So I take this, it turns into that, and that ends up being a battle of the big dogs. As n approaches infinity, the 6n is kind of useless. The powers are equal here, so I go to the coefficients. Bottom line is I get a value of 1/2, and 1/2 is in that golden zone, bigger than 0 but smaller than infinity. Since it's the golden zone, I can know that both series carry the same characteristics of convergence or divergence, and so I chose a divergent comparison series. That means my actual series is also divergent. Woo! Not bad at all. One more example. I look at this one. This one's a little bit messier, and at first you would say, man, I don't know that I could see a type of series that this looks similar to, but I'm going to show you some eyeball adjustment mental daydreaming. What I'm about to show you here is kind of like a little bit of intuitive algebra. There might be some flaws in the algebra, but we don't care because we're just trying to develop a suspicion. As I approach infinity and I think about the value of all these pieces, that 5 is going to become pretty inconsequential, so I'm going to ignore it for the purposes of creating a suspicion. And then if I think about the n and the 3n, as n approaches infinity, that kind of reduces to just be a 1/3 because this n and this n's, its power within the calculation seem to cancel out, which leaves a 4n in the denominator, which through a little bit of tricky algebra can be thought of as a 1/4 n. So with that type of situation, I can say this thing is kind of sort of like that, which by the way is a geometric series, and it's a convergent geometric series. This type of thinking makes me suspect convergence on that series. But Ron Burgundy might think that was voodoo, and you know what Ron Burgundy thinks about voodoo. If you don't, you might want to look that up. And if you don't know who Ron Burgundy is, shame on you. So there are my thoughts summarized. I've come to the conclusion that I'm going to not use that for a comparison series. I'm going to use that because that's just a little bit cleaner, easier to work with, and it's still a convergent comparison series. And it's still of the geometric form, which I thought this was kind of a convoluted geometric form, so it's a pretty good thing to do. I work on that limit. It's a tougher limit. It's a big old mess, but with some intelligent algebra trickery, I end up with a number of 1/3. By the way, I could have done the limit the other way, like I said before. I could be wrong here, but I think simply all would happen is your final result would be a 3/1. We could verify that, but ain't nobody got time for that. So I got a value that was between 0 and infinity. Since that's the case, my suspicion of convergence is confirmed. And we will say by the limit comparison test, our actual series converges. I hope this was more enjoyable than the direct comparison test. I think it was.